In this video, we're going to take a look at differentiating inverse hyperbolic functions. So to begin with here, if we begin with the first inverse hyperbolic function, if I have y equals arsinhx, so y equals arsinhx, and we differentiate this here, so dy by dx, and what I get here is 1 over the square root of x squared plus 1. So that's my first result there. So we differentiate arsinhx, the inverse of sinx, and we get 1 over the square root of x squared plus 1. And my next result here is for the derivative of arcoshx. So y is equal to arcoshx. So if I differentiate this here, again I'm going to get dy by dx. So dy by dx here. And again, it's pretty similar to this result. We get 1 over the square root of x squared minus 1 this time. Okay. In this case, x must be strictly greater than 1. Okay, so that's our second result. And then finally, if we have y equals artanhx here, artanhx, then if I differentiate this here, again we get dy by dx. Dy by dx. And in this case, we get 1 over 1 minus x squared. Okay. Again, we have a little restriction here. But there we have it. Okay. So those are the 3 results that we need. So now let's take a look at a couple of practice questions where we can practice differentiating inverse hyperbolic functions. So we start off here by taking a look at question 1. We've been given that y is equal to x cubed multiplied by arsinhx. And we're asked to find dy by dx. So what I need to notice here is we have a product of functions. I've got x cubed multiplied by arsinhx. So in that case then I can say that u is equal to x cubed. And v here is the remaining function, which is arsinhx. So if we're going to use the product rule here, let's just state the product rule. So dy by dx. So dy by dx, that would be u times the derivative of v. So that's going to be u v prime. And then we do v multiplied by the derivative of u. So that's going to be v u prime. Okay. So I also now need the derivative of u here with respect to x, and the derivative of v with respect to x as well. So if I differentiate x cubed here with respect to x, I'm going to get 3x squared. And if I differentiate v here with respect to x, I'm going to get 1 over. So 1 over the square root of x squared plus 1 there. Okay. Now I didn't mention it on the previous slide, but these results here for the derivatives of the inverse hyperbolic functions are given in the form of the book, so you don't have to worry about memorizing those results. So in that case now we can simply apply the product rule here. So u times v prime, so that's x cubed multiplied by 1 over the square root of x squared plus 1. I'm going to get x cubed all over the square root of x squared plus 1. And then I also have v here multiplied by u prime. So I'm going to get 3x squared arsinhx. So plus 3x squared arsinhx there. Okay. And there we have it. So that's our solution to question 1. So let's take a look at one more question here to finish with. We've been given that y is equal to arsin 2x all squared. And we're asked to show that 4x squared plus 1 multiplied by dy by dx all squared is equal to 16y. So the only real thing we can do here to begin with is just find dy by dx. Y is equal to arsin 2x all squared. So to differentiate here and get dy by dx, we need to use the chain rule. Okay. So the chain rule here will be 2 multiplied by arsin 2x, and we reduce the power by 1. That's 2 arsin 2x. But we're not done there, because what I need to do now is multiply this here by the derivative of the inside of the bracket. Okay. Now, we need to be careful here. So the standard result is for y equals arsinhx. Y equals arsinhx. When I differentiate that here, dy by dx, I would simply get 1 over square root of x squared plus 1. Okay, but we're differentiating in this case now, y equals arsin 2x. Okay, so two things to consider here now. Right, this will change my denominator, so this x squared here. So rather than it being x squared, it's going to be 2x all squared. So 2x all squared here, which in this case will simply give me 4x squared. Well, that's not too challenging, that's fine. But then don't forget we also need to use the chain rule here as well. And I now need to multiply that by the derivative of 2x, which would be 2. Okay, so dy by dx here is going to be 1 over the square root of 4x squared, replacing that x now with 2x all squared. So that plus 1 will stay there. That doesn't change. We now multiply all of this by 2. Okay. In that case, we're going to get 2 over the square root of 4x squared plus 1. So I can then multiply this here by 2 all over the square root 4x squared plus 1. Okay. So putting all that together then, we're going to get 2 arsin 2x multiplied by 2. That would give me 4 arsin 2x. So 4 arsin 2x all over square root 4x squared plus 1. Okay. Now this is for dy by dx. Okay, so it took a little bit of time to get there, but that is dy by dx. Now what I want to show here is 4x squared plus 1 multiplied by dy by dx all squared is equal to 16y. Now at this point here, I've got dy by dx. In this expression here, we have dy by dx all squared. So at some point I'm going to need to square this. And what I've also got here is the square root of 4x squared plus 1, whereas in this expression here, they've simply got 4x squared plus 1. What I'm going to do to begin with here is multiply through on both sides by the square root of 4x squared plus 1. So therefore, what we're going to get here is the square root of 4x squared plus 1 multiplied by dy by dx, like so. And that's going to be equal to 4 arsin 2x. So if we have dy by dx all squared, what I'm going to do now is square both sides here. So if I square the square root of 4x squared plus 1, that will simply give me 4x squared plus 1. We get 4x squared plus 1 there. I'm now going to get dy by dx all squared. That's all squared. And in this case then, if I square this here, that would be 16 multiplied by arsin 2x all squared. Arsin 2x all squared. But remember, arsin 2x here is equal to y. So arsin 2x all squared is y. Okay, so I can replace this now with y. So what I've got then is 4x squared plus 1 multiplied by dy by dx all squared. So dy by dx all squared, and that's equal to 16y there. Okay, giving us our solution. So as required, giving us our solution to question 2 there. And there we have it. So that's our solution, and that brings us to the end of this video on differentiating inverse hyperbolic functions. In the next video, we're going to take a look at integrating inverse hyperbolic functions.